Remember that every cell is bordered by a plasma membrane, that the plasma membrane is one of 4 basic structures consistent amongst all cells. The membrane controls movement of material into and out of the cell. We describe it as selectively permeable. That means some things can cross it, can permeate it, while others cannot. The membrane is depicted as a double layer of phospholipids. There are hydrophilic water-loving heads, and if we zoomed in, we would see that that phospholipid head is immersed in the outside world of the cell, largely water, or immersed inside the cytoplasm, also water. But the hydrophobic or water-avoiding tails create a thin limbo space. That's where the selectivity resides. The diagram also shows that these phospholipids are in constant motion. They can wiggle and move. They can also flip from inside to outside faces. So we describe it as a fluid model, constantly in motion. Recall the importance of fats, the biological macromolecule, and how we describe them as either being saturated or unsaturated. Remember that saturated fats were full of hydrogen bonds. And if we look at our diagram here, each carbon is bonded to just hydrogen, making them orderly, packable, structured. They're considered unhealthy because there's no gaps. It's hard to break them down. Unsaturated fats, in comparison, are bonded to carbon and oxygen too, other things than hydrogen, creating kinks where double bonds occur, making random spaces and pockets. These are considered healthier because they're much more easily digestible. Those spaces also help molecules move across and through the plasma membrane. And so every cell is composed of about 50%. And so every plasma membrane is composed of roughly 50% cholesterol to ensure that there are pockets in which molecules can transfer across. The cholesterol is the buffer of the plasma membrane. It maintains flexibility. It is able to behave differently at different temperatures. When things are warm, it holds the phospholipids together, keeping it from melting. When it's cold, it creates a little space, preventing it from freezing and becoming rigid. Cholesterol is an essential element of living organisms and living cells. In terms of public health, we sometimes say, oh, I've got high cholesterol, and that's a bad thing. What they're actually referring to is that you have a high proportion of the LDL form of cholesterol, which accumulates along blood vessels and can create blockages. But the HDL form is frequently broken down and recycled and moved back to the liver. This is considered good cholesterol because it can perform the necessary function of cholesterol, buffering plasma membranes without building up and affecting the circulatory system. There are many molecules embedded in the plasma membrane to help it perform its functions. Some of these molecules are described as transmembrane, meaning they go through one side to the other. Others are described as peripheral, meaning that they are one side only. They're either on the inside of the cell or the outside. These individual proteins have their own functionality. And that's where we get the term mosaic model for. The plasma membrane is riddled with proteins that are capable of moving stuff, doing stuff, sending messages, receiving messages, attaching. It is absolutely dynamic. Here we see that in graphical representation to try and make it memorable. But here we've got the same information more accurately drawn. Transporters are often tunnels or gates. Enzymes are just three-dimensional shapes with catalytic ability. signal molecules have a receptor side and a transducing side to pass on information. The molecules that recognize or join or attach have special hooks and attachment sites where covalent bonds can occur. One of the primary jobs of the plasma membrane is to facilitate movement. Recall that solvent refers to liquids in which things dissolve into. The solute is a solid or a gas that is dissolved within that liquid, carried across. The term precipitate might be new, and this is something that does not dissolve. It's something that it persists and sits at the bottom of the solution. We can see it depicted here in the bottom, a yellow solute dissolving into a blue solvent. And if we think about our art background, yellow and blue makes green. But if we were to zoom in on that green solution, we would actually see the blue solvent and individual single molecules of that yellow solute floating around, dissolved and dispersed evenly throughout that space. This slide summarizes the various types of transport that exists, the direction that they move, and whether or not there's an energy requirement to initiate that transport. Put a star next to this. You'll want to know these differences. You'll want to know these big picture details. Osmosis is the term for anytime water moves. And water will always move from where it's high, most abundant, to where it's low. Just think about how water moves from the mountain to the ocean. And this requires no energy whatsoever. We describe this as passive. Diffusion is when we move a solute. Passive diffusion moves from high to low, and the term passive again tells us that there's no energy requirement. Facilitated diffusion is a type of passive diffusion. However, it is assisted by some sort of molecule. Active transport describes the opposite effect, moving something from where it's low to where it's high, working against gravity or our concentration gradient, if you will, and that requires energy and effort. So in our depiction here, we can see an example of diffusion. A drop of blue dye into the water, and it moves from where it's most abundant, that single drop, to where it's least abundant, all those clear water molecules around, until it is completely dispersed. Same idea here depicted in terms of the dots, and we see the difference in terminology, passive versus active. Gradient refers to the difference from one side to the other. So in passive diffusion, we're going downhill, down the gradient from where something is high and abundant to where something is low. Whereas active diffusion, we're going against the gradient, trying to take those individual red dots and pull them back all together to create one single red dot of pigment. And notice that requires energy, strength, and takes a little bit longer. How do these molecules move? Well, really, it's the nature of the atoms themselves and their electrons. Molecules want to spread out evenly into available space. They don't want their electrons to be touching anyone else's electrons unless they're bonded. And so molecules move randomly, and whenever they touch, they repel each other, because two negative electrons, if you ever try to put two negative magnets together, there's a little bit of a buffer there. And so that pushes them away. And while all of this movement is completely random, over time, we see what looks like a directional movement as they find available space and evenly spread out. Our studies have shown that some solutes cross freely, quickly. Others require assistance, and some never cross at all. The ability to move across a membrane really depends upon the size of the molecule, its solubility, ability to be dissolved in that water, its chemical properties such as charge, polarity, and then the concentration gradient, the internal and external differences. The most permeable thing, the most readily transported, are small, uncharged solutes. The bigger it is, the more charge, the more likely it will need to be assisted. Facilitated transport increases the rate of movement of these things that might not move on their own, or it provides safe passage corridors across the hydrophobic phospholipid tails. Some facilitated proteins are channels that look like tunnels through. Some are carriers that open and close, facing the outside versus the inside of the cell as needed. Carrier proteins undergo a very subtle change in shape that moves the molecule they're carrying across the threshold. Not only can the plasma membrane distinguish what should move across, but it has a role in how quickly something will move across. The rate of movement will be affected by mass. Heavier molecules move more slowly than smaller molecules. Rate will be affected by temperature. Higher temperatures increase molecules' reactivity. Molecules are moving more quickly, and so they're more likely to cross the barrier more readily. My analogy at the bottom of the slide here is showing how sugar in hot tea will dissolve much more quickly than sugar in an iced tea, which tends to just sit at the bottom of the cup. Rates can also be affected by the solvent density. How thick is the liquid in which you're trying to move through? Moving through water is a lot easier than running through mud or maple syrup. The ability to dissolve into that water, break apart into smaller and smaller components, will also affect rate, because the more soluble you are, the quicker you can move. Overall distance, too, will affect rate. Do you just have to go a small bit? Because you'll get there faster than if you had to travel a long distance. And this is a throwback to the fact that molecules move randomly. They don't have directionality. They don't know which way they're going. They're just bouncing around and by chance crossing over into the cell that they need to be in. We see surface area to volume ratio again here, rate at which things move. And we see in life, in nature, that it is more energy efficient to be a big molecule, a big macromolecule composed of many small cells, than it is to be a single large cell. Because diffusion into every cell occurs at the same steady rate. But you'll cover more ground moving through small cells than you would through one large cell. And things are always moving. Movement continues until something known as dynamic equilibrium is reached. Dynamic, meaning there's still movement. There's just no net movement. And equilibrium, referring to the fact that the outside and the inside, that one side and the other have about even numbers. So in our diagram here, we can see the molecules of dye move randomly, some bouncing backwards, until there's even numbers of pigment molecules on the right as they are on the left, but molecules are still moving. And as one moves left, this creates less space and propulsion for one molecule to move right again. No net movement. In your reading, you would have come across the term tonicity, referring to how many ions or solutes are moving in that space. The thing to know about tonicity is that it is describing a scenario and a condition. The terms are arbitrary based upon what condition you're describing. So in the example below, we can see the first teacup is hypotonic because it has no dissolved sugar in comparison to the second teacup, which would be described as hypertonic, having more sugar than the first teacup. But if we describe teacup 2 to teacup 3, teacup 2 is now the hypotonic, having less sugar, than teacup 3, while teacups 3 and 4 are isotonic, having the same amount of sugar in their comparisons. Another thing to notice here is that there's a balance. Space is definite within the cell, and so if you've got more sugar, you'll have less water. If you've got more solutes, there's less water molecules. So there's a give and take. As the solutes move into one area, they'll be driving water out. So be aware that tonicity drives movement and that the water gradient is going to be opposite the solute gradient. Here we see 3 distinct situations. In scenario 1, we see a cell in a hypertonic solution. There are more green dots outside than there are inside. And so water is going to move from where it's most abundant, inside, to where it's least abundant, outside, trying to dissolve the outside world, make it safer, balance it out. Meanwhile, those green dots are trying to find space, and so they're going to be moving into the cell. The arrows depict the difference in gradients, so water is going to move much more quickly than the whatever the salt particle is moving in. In scenario 2, we now have a hypertonic cell in a hypotonic solution. There are less green dots on the outside than there are on the inside. So in this case, water is moving into the cell to try and dissolve the inside of the cell, while salts are trying to get out, or sugars. And in both scenarios 1 and 2, that movement is going to continue until we get to an isotonic scenario, where the number of green dots in matches the number of green dots out, and the number of blue dots in matches the number of blue dots out. As you can imagine, these changes can result in cell size and shape changes too. Putting a cell into a hypotonic solution means water is going to flood into the cell and potentially rupture it, like overfilling a water balloon. Putting a cell into a hypertonic solution means water is going to be leaving that cell rapidly, potentially deflating that cell. So our understanding of osmosis and diffusion and tonicity helps us to understand how movement will occur and helps us take advantage of those movements. When you go to a hospital and you get an IV drip, it is not solid water, it is a saline drip, 0.07% salt. Why? Because that is the percent tonicity of the red blood cell. And so what that means is that IV bag is isotonic to your blood cells. So that doesn't move across. Your blood cells aren't going to fill or deflate, but anything we add to that IV drip, like pain medication or antibiotics, that will move because that's the only thing that's different. And so that can help us better care for our patients and get them what they need when they need it. A moment to practice recognizing the relationship. The formatting convention is solution with respect to cell. Then identify the direction of going and where the solute's going. 6 different scenarios. The top panel describes cells in relation to an outside solution visually. So you can depict by arrow what's going in and what's coming out. The bottom table describes 3 scenarios without the image. So to practice imagining it in your own head, press pause, and when you finish working this out, continue the presentation. In our top panel, we can see that the cell has only 1% sugar, while outside is 5%. So sugar, depicted in green, is going to move in. But if there's 1% sugar in the cell, that means the cell's 99% water. Remember, because solute and solvent are inversely proportional. So water is going to be moving from inside to out. In scenario 2, there's more sugar inside. So sugar's moving out while water's moving in. And in scenario 3, it's the same amount of sugar on both sides. So we have an isotonic scenario. In our table, We can see scenario 1 is describing a hypertonic solution outside relative to the cell. So diffusion moves in, water moves out. In scenario 2, there's movement going both ways, of course, but salt is going to move in more rapidly as water moves out more rapidly. And then in scenario 3, we're talking about a hypotonic solution. There's less solute outside, only 8% solute versus 10% inside. And so diffusion is going to go out while water is going to flow in just slightly. Let's take a moment to talk more about active transport. The trouble with larger ions is that they're big. They usually have charge associated with them. They're usually bonded to other stuff, making it harder and clunkier to pass through those little pockets in the plasma membrane. So they require energy to get them across. We can break down this process of active transport into a primary transport phase and a secondary transport phase. The primary phase is the actual active transportation. It is the part that actually uses ATP energy to power the movement across. We call this the investment phase because you are investing energy in this movement, moving something against the gradient. But once you move it, it doesn't stay there. It's going to naturally move down the gradient through passive diffusion afterwards. So that's the secondary part of active transportation. It's actually the associated passive diffusion that results after the fact. But this is a payoff phase where we get to reap the benefits of that movement. Active transport needs transport molecules to move these things against the gradient. These transporters are described as uniporters, symporters, or antiporters, depending upon what they can move and what direction. Know the difference between them. And while it seems counterproductive to have a mechanism that requires energy to move stuff, when there are free mechanisms like osmosis and diffusion around, active transportation is essential to maintaining life because it is essential to maintaining the membrane potential. If we allowed diffusion and osmosis to run naturally on its own, eventually everything would be in dynamic equilibrium. And no net change means death to the cell, no new stuff coming in. And so active transportation is essentially a large reset button that then moves everything back to their big gradients and allows it to run again. Also, by being attached to an energy requirement, active transportation creates a regulatory rule, ensuring that things only move if and when certain conditions are met. And as we'll see in future chapters, that investment and payoff phase can be utilized to make energy, store energy, to create perfect scenarios that the cell can capitalize on with great efficiency. Sometimes things move as individuals across the cells. Sometimes things move in bulk. So I want to talk about the bulk transport of vesicles, exocytosis in comparison to endocytosis. Exo means exiting the cell, moving things out, releasing debris outside the cell. Endo means inside, taking things in. We further break down endocytosis into phagocytosis and pinocytosis, depending upon what they are bringing in. Phago refers to eating, so these are solid materials. Pino refers to drinking, liquid materials. A good way to think about this is Pinot Grigio is a wine, and that's a liquid that you drink.